Hi everyone and welcome back. So today we're going to be talking about limits and continuity as well as discontinuities. So hopefully you remember we talked about some of this stuff from the beginning of the year, what it means for something to be a continuous function, what it means for something to be discontinuous. So let's just get right into it. So one of the most important properties of the majority of functions that model real-world behavior is that they're continuous functions. So graphically speaking, and I'm just reading this right off of the page here, a function is continuous if there are no breaks at any given point of the function. All right, so a way that I kind of described this to you all from the beginning of the year is if you have to pick up the pencil to start continuing the graph, that means it's not continuous. Now from these pictures given here, so you have a continuous function, right? There are no breaks. There are no holes in the graph, right? Again, in a less mathematically said way, if I just were to sketch over this, I never have to pick up my pencil, all right? But now if I look over here for this next example, we have a removable discontinuity. And what that means is, well, it's discontinuous, meaning there is a break or a hole in the graph, which we can see. I continue here. I got to stop because there's actually no point here. There's a hole. We have a point here, and then we continue the function. So there is a hole in the graph. We call that a removable discontinuity because I can make this a continuous function by, if I wanted to, plugging the hole, which you're actually going to see in my next example. So in this example here, again, this is a removable discontinuity. There's a hole in the graph. But what I was trying to say earlier, right, I continue this, but there's no actual point here. But I can make this continuous by actually saying, let's say if I said to fill the hole by whatever that value is. So given this function, I can say, and given, you could have it as a piecewise function, to fill, so I would say f of a equals whatever that y value is, so say it's -2. So you have your entire continuous function with the hole, and you can actually plug the hole with a point to make it continuous. We're going to get to some examples of what I mean by that. All right. Next, we have a jump discontinuity, and then we have an infinite discontinuity. So these are the three discontinuities you guys need to know. Removable, jump, and infinite. So for a jump, it literally sounds like what it is. I continue my function, and then I have to jump to get to the next piece to continue the function. Infinite discontinuity, you have your vertical asymptote here. So we have the graph going towards negative infinity here, and then towards positive infinity here. We're going in two different directions. So whenever you see those vertical asymptotes, think the infinite discontinuity. All right, so that's just kind of a little summary here for the different discontinuities. So maybe pause the video here and see if you can match the graphs with their corresponding discontinuities. So we're looking for a jump. We're looking for an infinite discontinuity, a removable discontinuity, a jump, and then another removable discontinuity. So pay attention to the points where those are at and see if you can match up the graph. So pause the video here. You think you got it? So these are what the matching pair should look like, and I'll go through these just to do a little walkthrough. So for letter F, we have a removable discontinuity at x equaling 3. There's no jump here. Remember what I said from the beginning. You're not jumping to get to this point and continuing down. All right, we're just creating our function with a hole that exists at the point, and then there also exists a point as well here. So we just have a removable discontinuity when x equals 3. So when x equals 1, 2, 3, we have a point right here, and then there was the hole. So that checks out. Okay, let's see what we got next. So for what we have in green, there is going to be a jump. I'm going from one piece all the way up to the next piece of the function. So we know there is a jump, and it does exist when x equals 2. So when x is equal to 2, we do have a jump here. All right. And there's a removable discontinuity at -1, so that means there's a hole when x equals -1, and that is true. When x equals -1, there's a hole, and it's most specifically at the y value of -1, 2, 3, 4, at -4. And then lastly, we have our jump discontinuity at x equaling -1. So I had a jump at x equaling -1 to go to here. And we have an infinite discontinuity at x equaling 2, so that means we have that vertical asymptote here. Okay. Now, there is one more thing I do just want to bring up, is back at the top. I do just want to quickly go over how in these two examples here, for the jump and the infinite discontinuity, we actually also call these non-removable discontinuities. So what that means, a non-removable discontinuity, and I'm going to write that down here, non-removable discontinuity, is that limits don't exist at these discontinuities. All right, so I have that written there for you. I'm sorry for the handwriting. We have this as non-removable. So these two examples here for the jump and for the infinite discontinuity, they're non-removable because limits don't exist at these discontinuities, right? As we approach this value here for a from the left, for x, and then from the right, the limit does not exist. We're approaching two different y values. Similarly, with the infinite discontinuity, one of them is approaching negative infinity, the other is approaching positive infinity. So these are non-removable discontinuities because the limits don't exist here. All right. And then really quick, I do just want to point out again here that this was not a jump discontinuity. It's just removable because the function is in the same spot to the left and the right. So the function is still continuing in the same spot from the left and the right. There is just a hole that is here. Okay, now we can really just get into it. And you guys have the basis of what we need to start some practice. So let's take a look at exercise 1. So given the graph of some function f of x, we're going to state all the values of x in the open interval from -9 to +9 for which the function is discontinuous, and then we're going to state the discontinuity. So there actually is a lot going on here. So maybe pause the video here, start to highlight over the areas where you see the discontinuities, and I'm going to do the same. All right, so what I did was I just highlighted over the different pieces. So let's start with what I have written out here in blue. So let's go with what's in blue. And what we would call that, what I have highlighted here in blue, this is a jump discontinuity. So we're going to identify all these. This is a jump discontinuity. So the jump exists at x equaling -7. Because again, we have a point here when x is equal to -7, there is a point at -5 for the y value, and there's no actual point here for when y is equal to -1 at x equaling -7. So there's your jump. We have let's go to the next one, just going in order here. So in green, we have a removable discontinuity. So that's a removable, it's not a jump. And that exists at x equaling -3. So that's at x equaling -3. And we also have another removable discontinuity. We have another removable discontinuity right here at x equaling 1. So you actually have two removable discontinuities. You have it at -3 and 1. All right. And then lastly over here, what I have in red, that's our infinite. That's our infinite discontinuity. We're going towards infinity and negative infinity at this asymptote right here, this vertical asymptote, when x is equal to 5. So there you guys have it, when x equals 5. So these are just your different types of discontinuity. All right. You are going to do this one now on your own. This is an OYO. So pause the video here. See if you can, again, I would highlight over those areas of the discontinuities and we'll compare our answers. All right, so hopefully you got the same answer as me. We have our infinite discontinuity here because we would have a vertical asymptote. We have in red, there is just a hole here, so that's a removable discontinuity. And then what I have highlighted here in blue is actual jump because I had to go from this point, jump down here to continue the function. All right, hopefully we are getting the hang of this. Let's just get a little bit more practice here. So now we're just going to take a look at a little bit more vocabulary with limits and identifying where the function is continuous, evaluating the value of x specifically at the function, and we're going to figure out whether the limit exists or doesn't exist. So now this should be some review. So I'm just going to go through the first problem and then you guys are going to do the rest. You shouldn't really need my help here, but I'll go through the first problem. So we ask, is f of x continuous at x equaling -11? So -11, that's here. Is it continuous? Yes. There are no holes or breaks in the graph here, from here to here, so that's good. So we'll say, yes, it's continuous. What is the limit as x approaches -11? So as I approach from the left and from the right, we are approaching, that looks like about -1/2. And then what is f of -11? Well, there is an actual point there, so it is just -1/2. All right, maybe I'll just do one more with you, and then you'll do the rest. Okay, let's do question 3 together, and then you'll do the rest of these on your own. So for question 3, is f of x continuous at x equaling -2? So is it continuous? No. Why? Why is it not continuous? Well, because look, guys, you have a point here, and then this graph is going towards infinity. So we've got a jump going on. We're jumping from here all the way up to here and continuing the graph. So it's not continuous because of the jump discontinuity. What is the limit as x approaches -2? Well, again, we always have to check the left and the right. So I was looking here. Limit as x approaches -2. Well, let's see. And I'll erase what we got going on here to check out what's going on with the graph. All right, so as we approach -2, so we're approaching -2, I'm at the value of 3. So when x approaches -2 from the left, we're at 3. And then when x approaches -2 from the right, it looks like we're going towards infinity here. So the left-hand side and the right-hand side don't match. So the limit does not exist. And now I do want to evaluate what is f of -2. So is there an actual point when x equals -2? And there sure is. There's a point right here at 3. So even though the limit doesn't exist, there still is a value for f of -2. It is 3. All right, guys, fill in the rest of this chart on your own. I'll zoom out here so you can take a look at what we're doing. But finish this chart and we'll compare our answers momentarily. All right. Make sure you have the same answers as me. If you have any questions about this, please ask, and I will be very happy to go over any of this over Remind, whatever questions you have, or over Zoom. All right, so that just concludes this portion of identifying where the function is continuous, where it's discontinuous, being able to identify where those discontinuities lie, even thinking about what kind of discontinuity it is. And now we're actually going to fill out some information here on the removable, infinite, and jump discontinuities. So it's important for us to understand the true definition of what it means for something to be continuous. So in order for a function to be continuous at the x value, so let's just say when x equals c, and let me just sketch out for us here. So here is my function, and let's say this is x being c. All right, so in order for the function to be continuous, where again we have x equaling c, where c is a real number, well, the f of c must exist. So f of c does exist. The limit must exist, which it does as I approach from the left and from the right. F of c does exist, the limit. And then f of x, the limit of f of x has to equal f of c. So as x is approaching c, for the function f of x, we do end up getting f of c, which is true because that's when x equals c. Okay, an example of what would fail. So if I were to sketch this out again, and maybe we have something like this. And there we go. There's our graph. So f of c must exist. Well, let's see. Again, here is c. All of these limits have to be met, by the way. All of them. Not just one, not just two, all of them. Okay, so, well, in this situation here that I drew, f of c does exist. There's a point right here. All right, so we can check that off. The limit must exist. Well, let's see. As I approach C from the left and from the right, yeah, that limit exists. Okay, so far this is looking good. Now let's see. We have the limit of f of x. So let's say here, and this is my function f of x. So the limit of f of x as x approaches C. So the limit, and I'm going to make up some variables here. So let's just call this y value, I don't know, let's call that a, and we'll call that b. So the limit of f of x is approaching C, well, it has a y value of a, so that's going to equal a. And f of c is actually equal to b. Well, a doesn't equal b, so this would fail. So this part fails the conditions that need to be met in order for something to be continuous. So this was just kind of a counterexample showing you that a jump discontinuity indeed is not continuous. All right, so you guys are going to need to know these guidelines that I have here, the first, second, and third. All of these things are necessary in order for something to be continuous. So now let's just go through really quickly. We've kind of already done this, but just so you have this laid out in your notes nicely. A removable discontinuity or a hole could look something like this. All right, where this is my C value for X. And the reason for the discontinuity is, well, f of C doesn't exist. That means this right here means the empty set. Empty set, meaning there's just no solution. There is no answer. So it would make that actually a little bit neater. This is what the empty set looks like. All right. So for example, if this is my function f of x, well, at x equaling C, there is no actual y value. It doesn't exist. Y doesn't exist. All right. We get really close to whatever that y value is for f of C, but doesn't exist. All right, that infinite discontinuity, which is where we have the asymptote. Notice all these pieces here, guys. These are really important. So if I were to sketch this out, maybe this is what my graph looks like. And you have your asymptote. And this is where my C value lies. So there's C. We would have f of C, again, is equal to the empty set. Or, meaning there's just no y value, guys. We can't be approaching infinity and then also negative infinity at the same time. That's not going to work. Okay? Or the limit as x approaches C of the function f of x does not exist. Which again makes sense. You can't be approaching infinity and negative infinity at the same time. The limit would not exist. All right. And then lastly, that jump or piecewise function. All right, so maybe the graph looks something like this. So again, the reason why this would be a discontinuity for the jump would be if we were to evaluate this in limit notation. The limit as x is approaching C from the left and from the right does not exist because we're approaching two different values. So make sure you guys have this chart written out. This is going to be really helpful for us as we're going forward. Okay. Alrighty, if there are no questions, let's continue on. So you guys are actually going to be able to sketch the stuff out. You really don't need a calculator for this because you guys should remember from the beginning of the year how we graph rational functions. That's going to be really important with limits. So we're going to determine the x values for which the following are discontinuities when it's applicable, and we're going to state the type and the reason. So for the first example, and I'm going to walk through the first and second one with you, if you guys were to just sketch this is a line. So a line with the slope of 2, the y-intercept is at 3. So we're looking at something maybe like that, up 2 over 1. Well, that's continuous. There are no holes or breaks in the graph, it's a line. So this is continuous over the real numbers, which is from negative infinity to positive infinity. This is the symbol for real numbers, by the way. Real numbers includes from negative infinity to positive infinity. If I were to sketch this graph here, I'm looking at something that's cubed. If you guys remember, the leading coefficient is positive. This is an odd degree function. So my end behavior will be down, up. So if I were to sketch this out, maybe I'm looking at something like this. And again, This is also going to be continuous. There are no holes in the, continuous. There are no holes, breaks, etc. in the graph. So this is continuous over the real numbers. Okay, let's continue on. Question 3. So for question 3, I actually do want you to see if you can graph this on your own without me, remembering your rational functions and how to find that vertical asymptote. Pause the video here and see if you can come up with it. I'll post my solution in a second. All right, you think you got it? I hope so. You have the vertical asymptote here at x equaling -4. Remember, to find the vertical asymptotes, we set the denominator equal to 0. So I have x plus 4 equals 0. I'll have a vertical asymptote at x equals -4. So when I come over to sketch this, I'm at -4, that's here. Drawing my vertical asymptote. All right, this is what my graph looks like. This is bottom heavy, right? So this is bottom heavy. So we know that the horizontal asymptote is at y equals 0. So that's why we're never going to cross here. So that's what my graph looks like. And I just want to know the kind of discontinuity. So the discontinuity in this situation, so the discontinuity, this is an infinite discontinuity, infinite, and it occurs at x equaling -4. And the reason why that this is discontinuous is because the limit as x approaches -4 from the left and from the right of this function f of x does not exist. All right, so hopefully you have a similar kind of setup here for how we would have evaluated this. Okay, let's take a look at 4 and 5. Try to sketch 4 and 5 out on your own. You will be expected to do that without a calculator. So try to sketch 4 and 5 out on your own and we'll compare our solutions. Pause the video here. We're almost done. All right, so this is what your graph should look like, guys. Again, you're just sketching out your piecewise function here. We know that there is a discontinuity. So there's a discontinuity. There is a hole in the graph. Remember, this is not a jump. This is a removable discontinuity. So let's write that out. This is removable. Okay. And it's removable at, this is when x equals 1. That's where the hole occurs. And then there's a point here as well. So this is removable at x equals 1. And now the reason why we would say this is discontinuous using those rules above, remember it has to satisfy all 3. So the reason why this fails being continuous is because the limit as x approaches 1 from f of x, of the function f of x, it doesn't equal the value for f of x1. So if I were to call this right here, let's say this is my x1, and I'm taking the function for the limit of f of x. So as x is approaching 1, I'm approaching a y value of, let's see, 1, 2, 3. So this is approaching a y value of 3, which is not equal to f of x1, right? F of x1 here, if I'm using x equaling 1 as my example, when x equals 1, my y value is 0. So this here is equal to 0. 3 doesn't equal 0, which is why this fails being continuous. Because again, as the limit approaches 1 from the left and the right-hand side here, we're approaching a y value of 1, 2, 3. But my value for f of x equaling 1 is 0. These values don't match. Okay, last one, guys. Just try this one on your own. Again, you just got to graph it. And we've got one more question and we're done. All right, so I color-coded here how I sketched out my graph. Again, we want to talk about why this is discontinuous. So the reason for this discontinuity is because there's a jump. I have to jump from here to here. So this is a jump discontinuity at x equaling 0. And the reason why this is discontinuous is because if we take the limit as x approaches 0 for this function f of x, it doesn't exist, right? As I approach, let's go with a different color here. As I approach x equaling 0 from the left, I approach a y value of 0. And then as I approach x equaling 0 from the right, I'm getting very close to a y value of 1. So 0 doesn't equal 1, therefore the limit does not exist. And then lastly, I ask you guys to come up with a function that has a removable discontinuity. Remember, that means there's a hole in the graph. Hole in the graph. So think about when we did our rational functions unit and how we found the hole. So I'm going to give you an example actually here. So try to use this example to see if you can come up with your own. So if I have the function f of x is equal to x squared minus 1 all over x plus 1, I'm going to factor this. I'll have x plus 1 and x minus 1. When I factor this out, I see that the x plus 1's cancel. Remember, we said that if you cancel out the term of the factor on top and bottom, that means there's a hole when x equals negative 1. So if I were to now sketch this, and now this is my remaining function, y equals x minus 1, that's what I'm going to graph. So I'm going to graph at y equals x minus 1. So here we go, up 1 over 1. There's my graph. But now wait, there is a hole when x equals negative 1. So when I come over to negative 1 here, this should have a hole. This would be a removable discontinuity at x equaling negative 1. And the reason why this is discontinuous is because there's actually no y value when x equals negative 1. So when x equals negative 1, this actually has a hole here, so there's no y value. So again, I'll write our reason why this is discontinuous and removable is because at f of negative 1, it's the empty set. There's no actual value. All right, so you guys can come up with your own here. Just to give another example, if you were to come up with your own, you don't have to keep playing this if you've already got it. Make your own example right now. But you always just want to look for things that are going to factor. So another example I could have done, and I'm going to erase what I have on the screen, so if you want to, make sure you have this written down before I erase. Okay, this is just another example because, again, we can factor the top. And you'll see that you can cancel the x minus 3's, which again, that would indicate there's a hole at now x equaling positive 3. And my new function is y equals x plus 3. So if I were to sketch this, 1, 2, 3, 1, 2, 3. If I were to sketch this, my y-intercept is at 3. And I'm just going up 1 over 1. Up 1 over 1, but there's a hole at x equaling positive 3, so there's a hole here, remembering, because we just did this before. So again, the reason why this would be a removable discontinuity is because there, again, is no actual y value when x equals 3. So we would say f of 3 is the empty set. There's no actual y value here. Empty set. There you go. All right, guys, I hope you found this video helpful. This was a really important lesson talking about removable jump and infinite discontinuities. It's going to play a big role going forward for us.